Yes. 2 days ago on Wednesday, we considered Bayesian inference of a normal distribution based on the observation. And at that time, we considered only one parameter out of the, we know that we have 2 parameters for the normal distribution, and at that time we considered only one parameters by assuming the other known a priori. And at this time, in today's lecture, I will consider all the 2 parameters as unknown. And this is the more common case in practice. So it's more important than the things that are on Wednesday. The objective is the same. Estimates unknown 2 parameters, mu and sigma square here, of the normal distribution based on their observations. And always the same. At this time, we assume that we don't have any information about the prior. So we call it a non-informative prior. But because of the variance I told you previously, we, in this case, put the prior in this form, inverse of a variance. Then the joint posterior distribution is obtained by multiplying all the individual likelihoods, which is shown in this equation. So multiplication of each individual likelihood, and go through the process and rearrange in terms of the unknown 2 parameters, which are mu and sigma square. And at the end, we have this form of equation. So this is the posterior distribution for the 2 parameters, mu and sigma square. And within this, you can see the observation data, which are n is the number of observations, and s is the sample standard deviation, and y bar is the sample mean. So once you have the observations, you calculate these and apply those values here, then you get the answer, which means that the inference on the unknown 2 parameters in the form of this distribution. That is the answer for the Bayesian process. So I rewrite that expression here once again. This is the joint posterior distribution. But the bad news is that there is no inherent PDF function provided by the MATLAB for this. We don't have any function like you experienced, norm PDF, norm CDF, norm inverse, whatever. We don't have such function for this. We just have the expression. But at least we can take a look at this function in the form of shape by drawing on the MATLAB. So I will move to the MATLAB and take a look at the shape of this. You see, this function is a function of 2 variables, mu, and the other is the sigma square. So I will move to the MATLAB code. This is the MATLAB, and this is the MATLAB code. And I will assume we have 20 observations. And out of the observed data, let's say we have a sample mean 2.9 and the sample standard deviation 0.2. And based on these information, we draw joint posterior distribution using the MATLAB capability. So this is the information, and based on this, we put grids over the mu and sigma square domain and calculate the function values, which is the this equation as I showed you in the lecture notes. And once we have the function values over the entire grids, we can draw the whatever kind. For example, we can draw the contour of that function. Because this is two variables function, we can draw it in the form of a contour. So copy, paste, we get the answer. So this is the posterior distribution in the form of contour. So the x-axis is the mean, mu. Y-axis is the variance, sigma square. And this represents, as I always told you, represents the, our degree of belief on the unknown two parameters. And the area with the high values represents our high degree of belief, and the area with the low value is the less degree of belief. Also, we can take a look at the same results in the form of a surface three-dimensional shape using this function of MATLAB. And you can, using the MATLAB function, rotate the three-dimensional shape. So viewing at this direction, it shows you something like behavior of the unknown mu, because you look at the bottom line, varies from 2.7 to 3 point something. From the other side, viewing from the other side, you can also look at the behavior, something like about the variance, varying from 0 to something, another value. And again, you look at this in the three-dimensional direction. So this represents the posterior distribution of our two unknown parameters.
So as for the prior, why do you call it non-informative prior? Because the prior seems to be the function of variance. So I thought we have some idea about the shape of at least variance.
So on Wednesday's lecture, you asked me why I am saying this is non-informative prior, despite its inverse of variance. That is the thing that the statisticians do in this community. And I did not have time to take a look at the reason why this was so. So at that time, on the Wednesday lecture, I told the student that I cannot explain, I cannot answer to that question. So at this time, I'd like recommend you to use that. When it comes to the variance, use the inverse of variance as the non-informative prior. Okay. So this is a very important information about what we have to get for the posterior distribution. But this is not the end. Using this, what we have to do is we have to analyze this distribution, evaluate many things like mean of the unknown mean of the unknown variance, and standard deviation, confidence interval, and so on. So we have to evaluate those things based on this distribution. In order to do that, the first thing we have to do is make the marginal distribution out of this joint posterior distribution. which can be made by integrating out. We call this as the integrating out process. Integrating out the other parameter and get the distribution of single variable. And the other is the same. We call this as a marginal distribution. And in terms of the figure, this is nothing but something like I showed you previously to get the distribution like this for the mu, and get the distribution like this for the variance. And strictly speaking, what we are doing for the marginal distribution is to integrate over the entire range at a certain line and get a single value. Then it will be the PDF of the marginal distribution at this direction. So we have to conduct the integration to obtain that marginal distribution function based on these two equations. Once we can have that marginal distribution, we can move to evaluating the mean and confidence bounds, and we at the end get the answers what we would like to do. Also, we can move to the posterior distribution because we have the posterior distribution itself. I told you the posterior prediction is to predict the future new behavior in the form of distribution based on what we got for the unknown parameters here. And the equation is defined in this form. And this is the posterior distribution we obtained, and it is this one. And this is the new prediction, the likelihood of the new prediction based on the obtained two parameters. And multiply these two and also integrate out with respect to the two parameters. And the two parameters will disappear at the end, and we get the another kind of a distribution. This is called the posterior predictive distribution. We have to perform the integration for these two. Fortunately, we have to go through the integration process by hand and whatever, and we can get the answer in the closed form. And we have a specific function for this. So results of the marginal mean after integrating out the sigma square, what you have is this distribution. And this represents, after transforming the original mu into z here, then z will follow the t distribution with the degree of freedom n-1. The other one, the marginal variance, the same process. We go same process. In this case, we integrate out the mu, and in the end, we get this expression. Little familiar things that we learned on a Wednesday, 2 days ago. And also, instead of using the original variance sigma square, we introduce a transformed variable z, and z will follow the chi-square distribution. So we use these two information. We have the marginal distribution in the form of this one and this one. So we can take advantage of the MATLAB function for these and this, and calculate many things that we want. But before doing this, I'd like to review. I assume all of you are familiar with the what is the normalization, what is the standardization. But I'd like to review these things using the normal distribution and move to the marginal distribution. So again, I move to MATLAB code. So normalization means when it was the originally normally distributed with the mu and sigma, it can be transformed into the standard variable, very easy and familiar to you students. And with this, I will show the process. So let's assume we have a mu and sigma with these values. Then we can draw the PDF of the normal distribution like this. And this is the original variable, and this is the PDF of that variable. And instead of using this, we can transform the variable into the standard variable. In this case, I say this is Z. And in the transformed domain, I can also draw the same PDF. But in this case, the variable is a standard variable, so normalized. And the mean is at 0, and the standard deviation is always 1. But also, we can use this standard PDF to the original variable. In order to do that, we have to first calculate the standard PDF and divide it by the sigma. Then we can plot the normal standard normal PDF onto the original variable. We can see whether this agrees with the original PDF by running this command. This will be drawn in the red color, and the original was the blue color. And let's check whether we see the agreement, whether we see the red color replaces the original blue color. If that is the case, we have the agreement. So we have, instead of this one, we have another figure, which was the original PDF here. And let's see. Yes, the same figure is obtained, same curve is obtained. So we can make the original PDF in this way, but at the same time, we can also make the same figure by using the standard PDF and divide it by sigma and put it on the original variable, the same thing. So that's about the normalization process. So regarding the marginal mean, marginal distribution, I go through the same process. Remember that the marginal mean, in order to evaluate the marginal mean, we have to first transform the original variable into this another standardized variable. Then plot this using the t-distribution. And in order to do this in the original variable mu, we have to go through the same process. That means first we evaluate this is the next thing. This is the point that I have to do now. First, I use the standardized variable z and evaluate a t-distribution t-PDF based on this. Then I move to the original variable. And on top of this original variable, I plot the standard PDF, t-PDF, but in this case, divided by this item. By doing this way, we can get the marginal distribution using the standardized T distribution. Okay. Yeah, I will show you the results of the figure. And after closing the figure. So again, I show you two figures. First one is the just, in this case, T distribution. T distribution is always defined at the kind of a standard variable. And this is transformed into the original variable and to get the same distribution. And this is really the marginal PDF that we want. And with this process, we can also evaluate the cumulative distribution function value based on this process, or we can also evaluate the inverse of the probability distribution. For example, when we would like to evaluate the 0.1 inverse of the 0.1, which means the 10 percentile value of the marginal distribution of this mean, then we go through this process. First, we evaluate this function and get the z value and apply this equation to get the original mu. So I assume that everybody understands this. So in this case, what we see in the equations is the introducing a new some kind of a standardized variable. In the marginal mean, it was this one, and use the T distribution information. And in order to obtain the original marginal distribution, we have to go through the process using this information. The same thing applies to the variance too. Because we introduce another non-dimensionalized variable. In this case, z is this one. And a little different is, in this case, sigma square is placed at the bottom, at the denominator. Other than that, the process is the same. And we use this information. And this original variance that we like to evaluate is this one. But we have this function only. And through this transformation, we get the answer. So the marginal distribution, by going through this process, what we get is this is the standardized PDF. So the PDF at the transformed domain, and this is the original marginal PDF of variance. And I showed you in the three-dimensional shape, the marginal PDF looked something like a little bit non-symmetric form. And this is the thing. And next process we have to go to is the posterior prediction. As I explained a moment ago, the posterior prediction is defined by this equation. The posterior distribution and a new prediction, likelihood of new prediction, multiplying these two, go through the lengthy manipulation integrating process for the two parameters, mu and sigma square. It's a kind of a analytical derivation, and we end up with this equation. Although the process was very complex, the result we get is simple. And we see that the new prediction will follow this distribution. And this distribution represents, as always, the same. After going through the transformation from the new y into z, the z will follow the t distribution. Also, we can take a look at the shape of this distribution. Which is this one. This is the posterior prediction over new y. Explains that the new y will follow this distribution. And the biggest likelihood will occur here, and much less likelihood will occur there. For the new prediction, we have this information. And on top of this, we can also draw what was the posterior distribution of the mean. Marginal distribution it was. We can see that the red color is the marginal distribution of the mean, and the blue color is our prediction based on the observation we got. The prediction is much wider than the mean distribution. So no question means everybody understands. And I will move to the next part.
One question.
Yes.
What is the standard deviation of sigma squared? That is, the standard deviation of the mean is just simply divided by n from the original standard deviation.
Yes. Your question is what is the standard deviation of the variance?
Of the marginal of the variance.
When we say variance, that means the unknown parameter, sigma square. And this itself has the distribution, something like chi-square. And we have a distribution like this. And even within this distribution, we have the information like standard deviation or variance. And I didn't evaluate that. In order to do that, we need some much more mathematical calculations using the chi-square. Okay, I will move. To the simulation of the posterior distribution. Until now, I showed you the analytical form, analytical expression of the posterior distribution, and the method to evaluate many things like mean or standard deviation or confidence intervals using the resulting expressions. In this case, I will show you different approach, which is to use the samples. And you will find in the end this is much more convenient and much more powerful and applies to more general case. So I will start with this simulation process. In order to do that, one has to know what is factorization approach. In order to understand this, we have to review the joint probability of two events A and B. The joint probability, by definition, is given in this expression. And I hope you may be familiar already with this. This is the absolute probability of B, and multiplied to this conditional probability of A conditional on B. And in the earlier lecture, I told you about this. So we can have two ways. Either this or this may be used. The same thing, the joint posterior distribution for the two parameters can be written in the two ways. The first is this one and multiplied by this conditional probability. And you will see this and this is the same as the marginal distribution. And this is the conditional distribution, or the likelihood. And we will proceed the simulation process based on this equation. And at first, I will use the approach 1, which is to use the marginal variance, the first equation I showed you. And we already know what each distribution will look like, because this one is marginal PDF over sigma square, and I already showed you that this is the inverse chi-square distribution. And this one is a conditional PDF of unknown mu based on the assumption that we know sigma square. And this sentence that I told you now is familiar sentence because I addressed this thing on the Wednesday lecture. The case with one parameter when we assume that we know the other parameter. This is one of the cases. When we assume that sigma square is known and estimate only the mu parameter, this is it. And we already obtained the expression for this on the Wednesday lecture. And the result is this one. So we all